Our seminar today is Equity and Efficacy Using Data to Drive Transformation in Foundational STEM Courses. And today our guest speaker will talk about some of the research around structures and practices at research universities that have been found to drive away capable students interested in STEM, often in inequitable ways. He'll be reviewing some of that research, including a new multi-institutional, multidisciplinary results from a collaboration, and share his ideas and reform examples around increasing efficacy and equity in these foundational courses. So I'm very happy to welcome our guest speaker today, Tim McKay, who's joining us from the University of Michigan. He and his team have been using classroom and institutional data to make higher education more equitable, inclusive, and effective since 2008. And in the last few years, he's launched several projects and initiatives in those areas. So welcome, Tim, and I will turn it over to you.
Super. Thank you so much, Kristen, for the introduction, and thanks to all of you for taking the time to hear what I have to say today and to share your thoughts about it. I'm really looking forward to having the opportunity to do that with you today. I'm just going to share my screen and get the presentation going. Okay. So I am excited today to talk to you about this topic. It's something I've been working on in some sense for my whole academic career. And I'll say more about that in a minute. To give you an outline, what I want to do is introduce first the idea of these large foundational STEM and STEM-ish courses. It's not actually all just in STEM disciplines that this is happening. There are what I might call some STEM-adjacent disciplines that function in very similar ways and have very similar things happen. So we'll talk about that a little bit. I want to spend a good bit of time talking about the action we've been taking through a project that a group of us have been doing called Seismic. And so I'll be telling you about Seismic, work that we've done over the last 5 years at 10 schools with 200 plus people. And in particular, I'm going to give a few details about a recent aspect of that work called STEM Equity Learning Communities that has taken place across this network. And then, because it's always good to look forward to the future, I want to talk a little bit about Seismic 2.0, where this collaboration is going next, what the kinds of things are we're hoping to engage with, and how we hope to do it. Before I begin, I want to give thanks to the Sloan Foundation for providing really key core support for this project and for having the vision to enable us to engage in this work in this nationally connected kind of way. Before I start, let me give a little bit of background to give you a sense of where I'm coming from. So I am Tim McKay. I was born into a Detroit automotive family. I'm a first-generation college student. In fact, I was a commuter student for 4 years at Temple University. I worked in a grocery store while taking the train to and from school every day. I discovered at the end of my undergraduate curriculum that graduate school in physics was free. And that sounded like a lot more fun and a lot easier to get to than getting a job. So I went to graduate school at the University of Chicago, where I got my PhD in physics. I spent a few years at Fermilab as a postdoc, and then came to the University of Michigan in 1995. I am a professor of physics and astronomy and education, and now the associate dean for undergraduate education. And that little list of things is kind of the story of my evolution as a scholar. I was trained as a physicist. I spent 20 years doing research in big data cosmology and astrophysics. And then around 2010, I started to shift my research endeavors from astrophysics and cosmology, from using data about hundreds of millions of galaxies to try to figure out how they come to be the way they are. I shifted that research to using data about hundreds of thousands of students to try to figure out how students come to be the way they are. And in some ways, it felt pretty similar to me. I'll just give one example of that. An unusual feature of cosmology in natural science is that it is a purely observational science. You never get to do experiments. You don't create new galaxies or galaxy, universes. And education research is often very observational as well. Very, very difficult to fully control the environment and do deep causal inference in education. So I feel like there's some relation that seemed meaningful to me as I began to do big data work in education. A couple of features of this work: in astrophysics, I worked on projects like the Chicago Air Sour Array, and very formatively on a project called the Sloan Digital Sky Survey. And the Sloan Digital Sky Survey did two things for me. It got me deeply involved in doing big data cosmology. It was the first digital sky survey, the first big data cosmology project. But also, it was a really remarkable collaboration. a very open collaboration that taught me a lot about how to do projects across many institutions with many people in different roles at different levels, and how to make that inviting and successful for everyone who was involved. As you'll see, I've drawn a lot on my experience in the Sloan Digital Sky Survey for the creation of this seismic project. On the education side, I started out just as a teacher of large classes, and I would typically teach big introductory physics courses with 700 or so students. After a decade or a dozen years of doing that, I also became the director of the honors program in our College of Literature, Science, and the Arts, a program that serves a few thousand students within our 20,000 student undergraduate body. When I became the honors director, I started looking at data about students because I became an administrator of a program about students and realized how much data we had and started wanting to interact with it. That led me to get involved with our campus administration about learning analytics, about using data to understand the institution and the experience of our students and to try and improve it. That beginning of that work led through everything else that's happened since then. And I'll say just a few more words about that too. So there's kind of two beginnings for this seismic project. One was here at Michigan as we expanded our use of data, and the other is with the Sloan Foundation and other institutions. So let me talk first about things that happened at Michigan. A very important step for us was the installation of a real data warehouse in 1999. What this meant is that all the data about our students was now pulled together into one place. So at least in principle, it was possible to do a lot with it because it was easily accessible. It took a while for that really to begin to emerge. And it wasn't until about 2008 that we really started taking advantage of this data warehouse to do the kinds of studies that I'm talking about today. We began investigating, of course, because it was the course I was teaching, we began investigating physics courses and realizing that there were signs of inequity in those courses. Now, when I discovered that there were signs of inequity in those courses, I really wanted to know more about what was going on. And so I began working with our provost on the idea of opening up this kind of data for more of these studies. And when you go to a provost and say you'd like something done, they make you do it. So I was made the chair of a learning analytics task force charged with improving data access on our campus. We did a lot of things in that period that I think were really fun and formative. We created a symposium on learning analytics at Michigan so people could talk about all the projects that they were doing. We empowered a group of learning analytics fellows, getting them access to data, but also giving them financial support. We reorganized the university's data with a researcher's mindset at the heart of what we were doing. We built a kind of data release for researchers who wanted to study our students, something called the Learning Analytics Data Architecture, or LARC. And we set up a permanent committee to continue to study this data with the interest of student success in mind. And today that committee is called ASSET, Analytics for Student Success and Equity Transformation. We also started really working together on our STEM courses. This was partly supported by an NSF wider grant called Rebuild that connected us across our disciplines at U of M. So instead of just speaking in physics or just in chemistry, we started to talk across those lines, across all of the big introductory STEM courses. That was super fruitful. And so doing multidisciplinary work became a center of what we were engaged in. And then in 2018, we launched this thing called the Foundational Course Initiative. And I think it provides a great model for the kind of support that courses need in order to engage in serious transformation. This Foundational Course Initiative, which is funded by our provost, provides 3 years of support with a teaching and learning center for a course to consider what the challenges are that they would like to address, to make those changes in a pilot way in a second year, and then in the third year to think about long-term sustainability of those changes. So 3 years of support in the Foundational Course Initiative. So a lot of things were happening at Michigan. We were also in a lot of conversation with other institutions. And this was really driven by the recognition that we had widespread inequities in our introductory STEM courses. And we wondered if it was just a Michigan problem, or was this something that might be true for everyone? So we started by working across the Big Ten Academic Alliance, the BTAA. So I spoke to the Big Ten Academic Alliance provosts in 2013 about what we were seeing. And they asked what they could do to help. And I said, well, it would be great if we could make comparisons across institutions. And then in 2015, we launched a Sloan Foundation funded project called LARA, the Learning and Research Analytics Project. This led to a paper that I'll tell you more about in a minute in 2017 about patterns of gendered performance difference in large introductory courses. And then in 2018, in conversation with Liz Boylan, we went to the Sloan Foundation to present the idea of building a seismic collaboration and ultimately launched that in 2019. So seismic is the Sloan Equity and Inclusion in STEM Introductory Courses project. And you can see already that there are lots of acronyms in the work I do. I kind of like acronyms. This one is a slightly funny story. When I first came up with it, I thought it was too clever. And so when we sent in the proposal the first time, I used a more boring name. But I did mention to Liz Boylan that we had this other name, and she said, no, you have to use that. So we went back and decided to use it. So what is seismic? The central idea of seismic is to create a sustained multi-institutional, so more than one institution, multidisciplinary across all STEM disciplines, STEM education research and development collaboration, right? We really wanted to be able to work together across multiple institutions and do things together that we couldn't do alone. Central to the seismic project has been the notion that a course cannot be successful unless it is equitable and inclusive. In fact, that success in achieving equity, in being inclusive to all students, is the sign that a course is a successful course. All right. So equity was really central to, you can see it right in the name, right? It was central to the founding of this. From the beginning as well, this collaboration was inspired by the work I had done in the Sloan Digital Sky Survey to invite participation from everyone at each member institution. And this was inspired by these open collaborative structures in big data cosmology. When you create a space that enables people to do what they want to do and to do it better together than they can do it alone, then they're drawn to it and they come and participate in it. What they bring with them is a tremendous amount of energy and ability and expertise. So we were able to draw on more resources than we could ever have paid for by making people want to join it rather than, need to be hired to join. These are the 10 institutions that were involved in the initial seismic collaboration. 5 of them from the Big Ten, so University of Michigan, Indiana, University, Michigan State University, University of Minnesota, and Purdue University. 3 UC system schools, UC Santa Barbara, UC Irvine, and UC Davis. The University of Pittsburgh, and yes, Arizona State University. Our key collaborators in these early days at Arizona State were Sarah Brownell and Jim Collins, and I'm sure many of you probably know Sarah and Jim. I had the good fortune of visiting Arizona State a number of times, in part through the work we were doing together in seismic. All right, this is a picture of the first seismic collaboration meeting that took place in the summer of 2019. Now, the summer of 2019, that was a great summer. It was a lot better than the summer of 2020. You all will remember why that was. So this collaboration did undergo a big shift very early on in its progress. And I would say that shift was a mixed bag. Of course, we missed out on certain opportunities to do things together, but we also learned how to do things remotely much more effectively. And for a dispersed collaboration like this, that was very powerful. So I think we came through the COVID era relatively successfully. Okay, let's talk about these large foundational STEM courses, what they mean and what they're about. Seismic was launched to focus on equity in these courses because of several things. First of all, they have an inefficacy problem. These courses often weed out students who are perfectly capable of success in these fields, when what they should be doing is helping those students grow deep roots in the fields, right? They're meant to introduce students to the topic. They're not meant to drive them away, but they have the effect of often driving away students. They are not successful courses for many of their students. You can see this because they often fail their students. In most campuses, these courses have the highest DFW rates that you see on the campuses. What we do in seismic is we try to use institutional data to expose and understand the widespread, persistent structural inequities in these courses. And you can see this from this paper that I mentioned before, this paper that Becky Matz published in 2017 based on our collaborations across the Big Ten. It's about patterns of gendered performance difference in large introductory courses at 5 research universities. And just drawing from that paper, you can see the kind of conclusion. These results reinforce the importance of broad investigation of performance disparities across higher education. They also help focus equity research on the structure and evaluative schemes of these lecture courses. And we'll come back to that. I think the evaluative schemes are one of the key elements of structural problems in these courses. Okay. So what has Seismic been doing about this for the last 5 years? Well, we mostly bring people together, and we bring people together across disciplines. So this includes STEM and STEM adjacent social science faculty, and also education experts. We bring people together across roles. It's not just the STEM faculty members who teach classes who are part of our conversations, but very importantly, it's also students, including the students who are in those classes who are contributing to this conversation, and also the administrators who set the conditions for teaching in these environments, and the teaching center staff. And a group that we had not expected, but we're very fortunate to attract to this work was a group of diversity scholars. I'll say more about that in a minute. We also bring together people across institutions, the 10 public R1s that you've seen. Our work has been organized, as it was in the Sloan Digital Sky Survey, around a set of working groups that use equity data to focus on measurement, just trying to understand how to use data in an optimal way, on experiments, getting into the classroom and actually trying changes and seeing, using data, whether or not they're effective, thinking about the structures and constraints that are on these courses, and talking about the very constructs of equity and inclusion. So 4 different working groups working on all these different topics. Okay. One thing that happened to us is that by opening the doors and welcoming people in, we drew together a community that was much broader than we expected. When we started the Seismic project, it was a group of people like myself, STEM faculty members trained in traditional STEM disciplines who had been teaching for a long time and maybe developed some teaching expertise, but really STEM faculty. And by having this focus on equity and an open collaborative model, we drew in other people who we didn't even invite. We just made it possible for them to join, and they came, right? So students, faculty, and staff from all the STEM fields and beyond. And we found over the course of this that contributions from social science and education and diversity scholars have really been crucial to our work. They've really helped us understand what it is we're really doing. There's deep expertise there that we really needed. And so we've actually written quite a bit about these things, on thinking about how to create the infrastructure for multi-institutional innovations, thinking about critical approaches and their role in doing STEM equity work, and thinking about things like systemic advantage. So I'll talk a little bit more about the systemic advantage work before we're done. That was an important thing for us. To be open and welcoming paid off in a really big way for us. Okay, let me give one example of both the inefficacy and an element of the inequity present in large STEM introductory courses. This is data that comes from the Big Ten Academic Alliance, a project that was done within the APLU called Powered by the Publics. This is a group of universities, you can see them on the upper right, drawn from the Big Ten, who gathered up information about DFW rates in many of their large introductory science and math courses. The first thing you can see in this figure is that the average DFW rates for these courses are quite high. Many students do not successfully complete these courses. In a way, that's a sign of the course's inefficacy. It should be possible to introduce all the students who are at these campuses to a subject like calculus. It is possible to do so, but these courses are not successfully doing so. A lot of students are not successfully completing these courses. So that's a first sign of an issue. But this study also made some comparisons of different groups of students and found that there are substantial and various outcome inequities in most of these courses. And to take just one example here, the average General Chemistry 1 course in these universities has a 23% overall DFW rate. But if you make a comparison between majority and minority students, the majority rate is about 21% and the minority rate is about 31.7%. You can see similar differences across some of these other dimensions of income, of first generation or non-first generation, and in some cases, gender differences. Not in all cases, but in some cases, gender differences. Okay. So this is the kind of pattern we were looking at. that led us to launch Seismic and to engage in this kind of work. All right, so let's just look at one example here, this pre-calculus one. It's an interesting one because it shows that although this course has efficacy challenges, right, a lot of students are not successfully completing it, it's a relatively equitable course. The outcomes don't vary much across these, different categories. So by looking at patterns like this, we can ask questions about what's going on in these classes, how are they structured, how are they taught, what might it be that is related to the inequities that we see. By being able to make a bunch of comparisons like this, we hope to be able to find the bright spots where there's something going on that's working well, and to learn from that and try to use it to make changes in other places. I'll talk more about those at the end too. Okay, so how has Seismic advanced our understanding of these structural advantages? Because we have access to really rich student data about many comparable courses on many campuses, we've been able to show that current course designs advantage some students and disadvantage others. In the sense, they're made to work well for some students and they're not made to work well for other students. The intersecting effects of these advantages reveal ways in which structural factors drive student outcomes, and I think they help to point to solutions. So let me talk about 4 common factors that we see providing advantage in many cases across these kinds of introductory STEM courses. One of them is about being first gen or not, or having access to college knowledge, you might say. Many continuing generation students have good access to that kind of college knowledge, while first generation students don't. That's an advantage if you have access to that college knowledge. Another kind of advantage is access to significant financial resources. This can create space and time for you to do more. It may also have created space and time for you to do more in the past as well. So you are set up in a different kind of circumstance, both in your preparation, but also in your current moment. Another advantage might be membership in a dominant social group, a social group that finds it very easy to feel welcome, supported, and engaged in an educational environment. And finally, a fourth possible advantage is access to prior preparation in an introductory course topic. All of those are things that might play out as elements of advantage in these large foundational STEM courses. Let me just show you how that might work. One example. This is moving beyond just looking at gender for thinking about equity and looking at a variety of individual dimensions of possible advantage for students in a single course within some seismic analysis. What you're looking at here is average grades for people who either do hold an identity with the triangles or don't hold that identity with the circles. So if we were to look at the student identity of woman, we would see that female students receive grades represented by the triangle here. Male students receive grades represented by the circle here. And if you look across these dimensions, some of them show up as a sign of advantage. So being a continuing student rather than a transfer student is an advantage. But being an international student is not an advantage, right? There's no real difference between being an international student and not. So for a course like this, we might identify a set of dimensions of advantage within the context of this course that would be things like this. So like being a high-income student, being a continuing generation student, being a male student, and being a majority student. Okay. How do those dimensions of advantage intersect with one another? Like, do they all contribute or not, right? So we've done a bunch of work to try to understand how they work together. I'm going to step aside from that just briefly to talk about how we test for outcome inequity in a course where students are diverse. If we want to focus on the impact of a particular course on student outcomes, we might want to account for students' general success in the college context, right? So we're trying to figure out, is this course worse for these students, better for these students, or about the same as other college courses? We do this by using their GPA in their other courses, or GPAO, to provide this. This GPA in other courses is the strongest grade correlate and the best predictor of grades for everyone in college. It's also kind of a performance referent used by students. You know, if a student comes into a class and says, I'm a 3.7 student, and then they get a B, they're going to feel like this course they really didn't do nearly as well as they usually do because they're referring it to the GPA that they're used to getting. Okay, so the impact of a course can then be represented by something we call a grade anomaly that it presents to students. It's very simple, but it's an important kind of conceptual idea for us. It provides insight to the performance variations which are local to this particular course, right? And they're often experienced that way by a student. Wow, in this course, I did really differently from what I usually do. So all the grade anomaly is, very simple thing. It's what this course did to the student compared to the effects of college more broadly. And if this course is about the same, these grade anomalies are zero, right? Okay, so let's look at that grade anomaly. That's what we're seeing here now on the x-axis. The grade in this course minus students' grades in their other courses. And we're looking at a whole set of different advantages here. The advantages would be being male, continuing generation, not a peer student, or a high income student, all right? And we now are recording something called the Systemic Advantage Index for these students, which counts how many of these advantages they have. And they may have none of these advantages. They may have just one of these 4 advantages. They may have 2, 3, or 4, right? And so when we look at this, what we can see is that all students pay a grade penalty in this course, a grade anomaly. Right? All students have an average grade which is lower than their grades in their other classes. This is quite common in STEM courses. But that grade anomaly varies for students with different levels of advantage. And if you just look right down here, the gender differences from our original studies are just the points that you would see in this box. So everything else we're seeing here is showing us more information, things we were not seeing in our original analyses because we weren't looking for these other axes of advantage. So what you can see is that there's a general shift in grade penalty paid in this class with the number of these advantages that students have. All right. So going beyond the binaries, we started looking at this systemic advantage index, where the idea was to identify meaningful advantages by examining each dimension of difference and then exploring their intersections, including by calculating this systemic advantage index. We define that as just the number of these advantages that students have, right? What we just saw in that figure. What's nice about this is it does 2 things. If you look back at this figure, there's a lot of detail in this figure, but there's also a basic fact that all of these elements provide advantage and that they aggregate so that the inequities in the course become larger and larger as you have as you have more of these advantages. Okay, you can see that much more clearly in a figure that just looks at systemic advantage index. So this is just the count of how many of those advantages students have. Do they have none of those advantages, one of those advantages, 2, 3, or all 4 of those advantages? And a figure like this makes the kind of aggregating power of these advantages much more apparent, I think. And so we found as we were discussing within our own institutions how to think about this, that this kind of systemic advantage index approach was a way of us showing that this course really does provide these kinds of systemic advantages and that they're quite strong and stark. And remember, this grade anomaly is already accounting for grades in all other courses, right? So if this course just gave lower grades but had no inequities in it, all of these would line up at the same place, right? The same vertical line. So we're seeing not only our grades lower in this course, but they are systemically lower and inequitably lower for groups of students. Okay. And the size is pretty large. You know, we're talking about a half a letter grade advantage for students across this range of advantage. We just found this way of looking at it a much clearer representation of how advantage accumulates to students. So we've been using this a lot internally. Okay, let me give one more example. This is from the last 2 years of organic chemistry at a large Midwestern university, and the advantages here are being male, being continuing generation, and being not an underrepresented student. This is organic chemistry, so lots of students take it. In 2 years, we had 3,800 people take it. The overall DFW rate for this course was about 30%. For students with all 3 of these advantages, about a quarter of the students The DFW rate is substantially lower, 5% lower, 24.7%. For students with just two of these advantages, the DFW rate jumps up a lot from the 30% to as much as 48%. For students with only one advantage, they're all over 50%, the DFW rates. And for students who possess none of these three advantages, the DFW rate was 71%. So this is a course set up to introduce people to organic chemistry, and a group of 106 students who lacked these three advantages in the class, 71% of them failed to successfully complete the class. It's an almost impassable barrier, right? And if we weren't looking at these intersections, we wouldn't see the extent of this. We might have only noticed, oh, there's some little inequities, right? We wouldn't have seen how much those pile up and how serious they become for students in the class. And it's that kind of recognition that has helped a lot of my colleagues finally say, okay, we're really going to have to make changes, because they'd never wanted to put a kind of impossible barrier in front of students. They really don't. Okay, so what's the lesson here? Advantage operates across many different axes of difference, and introductory STEM courses regularly provide special advantage beyond those which are typical in higher ed. Remember, we're accounting for the kind of general overall advantage that students might have. It's providing advantage to wealthy white continuing generation students. And STEM courses are making this worse, right? Like significantly worse than the rest of college. So we have a special role, an important role to play. In many disciplinary contexts, they also provide additional advantage to male students, not at all. And that's one of the interesting things we've learned. Context matters, that's what I'm saying about that the traits which provide advantage vary, and we can learn something from that. And we should be working on that. Okay. Another thing we've learned is that seismic doesn't need to fix students. We spent a lot of time in our first 5 years, frankly, thinking about interventions, student support interventions of many kinds. Sense of belonging interventions, work on how students engage with and use office hours, interventions, social psychological ones like values affirmation interventions, considerations of instructor representation, things that might help a group of students in a class without changing the class. Right? And these attempts to protect and support students, that's the idea. They're trying to protect and support students who lack advantage within systems that are not really designed for them. Now, one thing we learned in the course of these experiments that we did in seismic was that these kinds of interventions can and do have some impact, but they don't address the root causes of inequity. And more important to that, they tend to be very fragile. So if you set them up and you run them very, very carefully with a lot of support, they can have a pretty good impact. But you have to make sure that every time you're going to try to get that impact, you have that very, very careful application and good support. So they're not, in a way, a long-term solution to this problem. What we'd like to do is fix the root causes and get beyond that. Okay, so where's this work headed? A first thing that we're particularly concerned about is changing faculty attitudes about equity. We need to end the sense that introductory courses are supposed to weed out students, and to own the fact that the purpose of these courses is to successfully introduce students to disciplines. We also need our communities to recognize that persistent inequities in higher ed are signs that our systems and structures have failed students, not that our students are not adequate. So to make lasting progress on equity, we think we need to focus on making structural change in these large courses, and we need to change faculty attitudes to be able to do it. So what are we doing about faculty attitudes? We have to leave behind these student deficit models that I had in the past and that I think many people still possess. Many instructors blame these kind of variations in course outcomes on students. They think it might be a difference in their effort or their background or even their ability. And if we're going to get them to really make a change here, we're going to have to overcome these deficit explanations. We need to help faculty see the structural origins of persistent inequities and to help them recognize these as course deficits rather than student deficits. If a course isn't working for many or most of its students, it's not a very effective course, and we need to change it. If it's being very inequitable, it's not a very effective course, and we need to change it. So we're working on how to change faculty mindsets about the origins of inequity right now. I'm going to skip over this and talk about ways we're using equity data to change attitudes of faculty. through STEM equity learning communities. We think that because STEM faculty are data people, data can be a key tool for changing faculty attitudes and for driving change. That's really actually been a seismic tenet from the start. We've always believed that. Over the last couple of years, seismic institutions have piloted STEM equity learning communities as a model for supporting faculty through this process. This grew out of a number of our individual institutions doing related things. Here at Michigan, we were doing course equity reports, and UC Davis was doing a project called Know Your Students. Marco Molinaro was involved in that. UC Irvine had a project called Compass, right? So we were all doing something like this, and we brought it together to try and see how we could do it across institutions. Doing this well requires a lot of time, it requires effort and some special care, because we really need to help faculty avoid drifting toward that deficit mindset and focusing on structures. And we needed to be careful about measuring equity, intersectional equity, in a responsible way and including student voices. So we've been working on an NSF-IU's grant to do this work over the last couple of years. What we did was to form SELC teams at 9 universities across the country. The process of forming a team requires bringing together at least 4 STEM faculty members from mostly from one discipline, but in some cases from across disciplines, with undergraduate students as members of the team, and then supporting that team with a data analyst so that the team can ask questions and get answers provided by the data analyst, and with a facilitator to make sure that they have the kind of infrastructural support that they need to be able to meet in effective ways. This process took place through the 2023-2024 academic year. We kicked off with a May meeting at UC Davis. Then during the year, there were 8 local SELC meetings on each of the 9 campuses, plus 4 inter-SELC meetings that took place remotely across the campuses. And the process concluded with each of these STEM equity learning communities making a presentation to their local community about what they'd found and making recommendations about changes that they would like to see. So how have SELCs benefited from Seismic's open collaborative model? What we did was to come together as a team to prepare code for course equity reports, share that code through GitHub, and define a simple format for local data on each campus. So essentially, we made it really easy for everyone to have the same kind of equity reporting on their campus without needing to do a lot of extra work. Then as the SELC data teams met in UC Davis, they were able to plan their projects and conclude in May of 2024. And there's a SELC description paper that will be coming out shortly in the To Improve the Academy Journal of the POD Network. So working on changing faculty attitudes. Here at Michigan, we're continuing that department learning community approach, bringing in some elements of department action teams, the department action team model for change, and working with departments over a year-long process that's modeled on the SELC environment. All right, let me spend the remainder of my time talking a little bit about what kinds of structural changes we need to make. I think that some of the shared structural constraints that these introductory STEM courses possess are so long-standing that they're hardly visible. I mean, they seem intrinsic to the courses rather than being choices. They are the kind of norms and expectations for what constitutes a university introductory STEM courses. And they exist both in the courses and in some cases in the structures that surround the courses. So I'm going to talk about a few of these key systems and things that we're working on modifying within the seismic collaboration. So one example will be placement in courses. I'm going to talk about content mania and curricular expectations, about pedagogy and modes of instruction, and especially about high stakes exams and assessment of learning. So placement. When should students be required to take our courses? Now, this question has been out there for a long time. There are answers on all of our campuses. I think many of those answers have not been examined very much very recently, and that we should look closely at them. I'll give you one example of a way in which this becomes complex. On our campus, sometimes our faculty are quite skeptical about things like AP scores. So they say, well, you got a high AP score, but I still want you to take our introductory course because our course is so important and so good that you should take it. Now that sounds like a good idea, but what it means is that in the course, you're going to have students who have taken, let's say, physics for 2 years in high school and students who have never seen it before. And when you try to teach a group of students that has both of those traits, It is very difficult, and the tendency is to teach a course to students who've already studied it a lot, and to create a course that's actually functionally impossible for the students who've never studied it before, right? So the placement of students in these courses is an important thing. We did a study of this in the seismic collaboration, looking at advanced placement scores on a bunch of different university campuses. And there are cases where a student has an AP score and still takes the introductory course and goes on to subsequent courses. And there are cases where a student who has an AP test score skips the introductory course and goes on to subsequent courses. And in this paper, we found that students who skipped their first course with AP credit actually performed similarly well or better in subsequent courses than did students who did not skip, even in contexts where lower AP scores were accepted. One way of summarizing this would be to say that taking a high school AP class is as good as or better than taking the introductory course we're teaching in college. That's a distressing conclusion to reach. And I teach these classes, right? I don't feel like that's the way they are. But there is evidence to suggest that they kind of are. They're not doing the preparatory work that we think they're doing. They're not making a big difference for students. So thinking about placement. This placement point interacts with content mania. We all know what I'm talking about here. The idea that an introductory course must cover every conceivable topic, right? This argument for content coverage is usually that students need to know all of this for their subsequent classes. And so it would be a fair question to ask whether students really do know all of this when they take our class. And I would say it's unlikely that they do. One way we see this is that a lot of introductory science and math classes have quite low mean exam scores. Right? If you give a test in your class and you're asking questions you expect students to be able to answer, and the mean score is 50%, something went wrong, right? You can blame the students if you want, but it didn't work one way or another, right? We also, I at least, also experienced persistent complaints from instructors in subsequent courses, like, didn't you teach them this? And then we would go back and say, no, look, it's here, it's on my slide. I did, I taught them this. But having taught them this doesn't mean that they know. So we're not the only ones beginning to recognize this. There is this excellent paper from Kim Tanner's group with this title that I love, Content Coverage as a Persistent Exclusionary Practice. And what their point is in this paper, that we're cramming all this content in, and when they went to figure out, do these students really need to know this? They found out they don't. So it's almost like we built this content mountain to stand in the way of students who don't even need to know it. So there's some serious questions for us to address about this. Now, some students do seem to learn everything in our intro courses. Why might that be? Well, maybe it's because they studied it for 2 years already. Right? So again, a thought that might undermine our sense of the success of these classes. High stakes exams, I'm not going to go on too long about this. The evaluation of student learning through high stakes exams is a long-standing and problematic practice in these classes, I would say. First of all, high stakes exams like this are inauthentic. Nobody takes a high stakes exam like this as a scientist further in their career, right? It's just not an authentic measure of student knowledge. Very often we create reductive things in these exams. Physics is very guilty of this, presenting students with puzzles that are not real scientific problems and that trivialize science, systems with no friction, whatever it might be. It's often the case that these are multiple choice exams where correct answers don't require any understanding at all. They require filling in the right bubble. So it's possibly to get a perfect score in a completely inauthentic way. Right? I mean, a good evaluation of learning wouldn't have that trait. Time constraints like the ones we have are frankly kind of bizarre. Again, we don't use them in other contexts, so why should we do it like this? And I've come to think, too, that here at Michigan, we use evening exams for a lot of these classes. And boy, that's another set of problems. I mean, not all of our students can just show up in the evening. Right? Evening is not the perfect time to show up and take an exam, not even for a student, right? Anyway. Lots of issues with high stakes exams, and we're thinking really hard about how to make changes to them now. Yeah, I mean, what do you need to do to get it right? You have to mark the correct answer. You don't have to actually know it. You just have to mark the correct answer. Okay. So what might changes in structure look like? I'm just going to point out a couple of examples of recent papers that talk about changes in structure that I think are really interesting. There's a nice Webb and Paul article from the Physical Review Education Research Journal talking about two example changes to structure in physics courses at UC Davis. One of them is to change the way it's taught, so to decouple the conceptual understanding of physics principles from mathematical manipulation of equations. We usually, in our physics classes, run these two things together. And so students are both trying to understand what's going on and to calculate. And those are both challenging things. And when we dump them both on them, they may struggle with one, and we might think it's about the other. It's hard to tell. So what they did was to teach the whole class even faster than usual, conceptually at the beginning, and then come back around and put the mathematics in. No change to the subject matter, just a change to the way of teaching it, right? So that's one example, and they found that significantly reduced equity gaps in the class. So a change to structure that leads to the kind of outcome hoping for. Another change that's become much more widespread, and I hope will continue to, is changing from one and done examination schemes, which are really summative and don't provide students with any feedback, to examination schemes that are learning experiences, something closer to mastery learning experiences. People do this at many levels. There are two-stage exams sometimes people do. In the case of all of our introductory math courses here at Michigan now, we use actual mastery testing so that students can, on every skill that they're trying to develop, can multiply test until they can demonstrate their knowledge of that skill. Right? So the point is to get them there. It's not to check once and see if they're there, but to help them get to the point where they are there. So both of those are interesting examples, I would say. So what's next for this seismic collaboration? We're about 5 years old, and we're now in conversation with the Sloan Foundation about Seismic 2.0. And our goal is to recommit to our main goals, to refine the institutional commitments for our members, and to continue our pursuit of additional funding for the collaboration, which we've been very successful at doing. A key thing for us is to maintain the open community of opportunity that Seismic established and to really focus on continuing to involve students in what we do. They've been so helpful in our understanding what's really going on in these classes. We are inviting more institutions and involving more disciplines, especially the quantitative social sciences. And I'm thinking here about economics first, a place where very similar patterns appear and very similar structures are used in courses. We're also hoping to expand our impact beyond seismic member institutions through open projects like the Silk project and so on. And I'm going to leave up some thank yous here at the end, and I will stop speaking now and see if there's a little bit of time to answer your questions.